Quadratic equations are used in many real-world applications. For example, you can throw an object, projecting an object, diving, jumping, etc. You can also use it in area, because area is a square unit activity, so it can be used to provide us with some quadratic fun. So looking at our first example right here, we have the area of a rectangular piece of cardboard is represented by the equation W times 2W plus 3 is equal to 9, where W is our width of our cardboard in feet. So find the width. Well, to start with, I'm going to take my equation here and I'm going to simplify by using the distributive property. So I'm going to take and multiply the W times each of these pieces. So I now have 2W squared plus 3W is equal to 9. I'm going to move the 9 from the right side to the left side by subtracting 9 from both sides of the equation. So I now have 2W squared plus 3W minus 9 is equal to 0. At this point, I want to see if I can factor it. In order to factor it, I'm going to take and use the method where I multiply A times C and find out if there's anything that will add to B. Well, this is my A, my B, and my C. So 2 times negative 9 gives me negative 18, and that has to equal 3. So I have to figure out what can I multiply to get 18 but subtract to get 3. In this case, it will be negative 3 times positive 6, because negative 3 plus positive 6 gives me a positive 3. Replacing the middle term, my B term, with a negative 3 and a 6, I now have 2W squared minus 3W plus 6W. Those are the two that I just found from right here. Minus 9 is equal to 0. I can now use my factoring by grouping. Out of the first two, I'm going to take out a W, which leaves me with 2W minus 3. Out of the second group, I can take out a positive 3, which leaves me with 2W minus 3. Since both of these pieces are the same, I can factor those out. 2W minus 3 times W plus 3. Set each piece equal to 0. This here, the one on the left, I add 3 to both sides. And I have 2W is equal to positive 3. I divide both sides by 2. And I see that W is equal to 3 over 2, or 1.5. Now my other piece over here, when I move my 3 to the right, I get that W is equal to negative 3. Since this is a measurement of width, width cannot be negative. Therefore, this is an extraneous solution. So my width of the cardboard is 1.5 feet, or 1 5/10. In this example here, Johnny throws a tennis ball into the air as far as he can. We have the following function, which is given to us here, expressing a function of t where x represents the number of seconds since the tennis ball left Johnny's hand, and f of x represents the height of the tennis ball in feet. And we model it by the path shown here with this parabola. When we go to solve this, we can take and label everything. So first we want to find what's my y-intercept. Well, the y-intercept, remember, is the c value in my equation. Because remember, if I go and find my a, b, c's, a is -4, b is 8, and c is 7. So my y-intercept is 0, 7. And I can start that as my first point. Next, I want to find the vertex. To find the vertex, I'm going to use this equation right here that'll find my axis of symmetry. And then I can use that as the x value for my vertex. So x is equal to the opposite of b over 2a. I go and I plug in my a and my b. So on top I need b, which is 8. On the bottom I need my a, -4. So I have -8 over -8, which in this case gives me a positive 1. 1 is my axis of symmetry. I can come over here and I can place a dotted line here for the axis of symmetry. To find my y value, y is going to equal -4 times 1 squared plus 8 times 1 plus 7. We substitute it back in to our original function. Here, y is equal to -4 plus 8 plus 7, which gives us 11. Now that I have that, I know that my vertex is located at 1, 11. So I can come over here on my graph. I'm over at 1 on my axis of symmetry, and I go up here to 11. I know that there's another point exactly the same distance from the axis of symmetry as my y-intercept. Now, the graph cannot extend outside the first quadrant. So what do you think this may be? Well, remember, along my x-axis, this is my time. And this one here, this is the height of the ball. Since I cannot have a negative measurement and I cannot have negative time, we have to keep everything in the positive realm. So time and height cannot be negative. So everything stays in the first quadrant. So we need to go now and find our x-intercepts. To find my x-intercepts, I take my original equation and set it equal to 0. Here I want to go through and find, using my AC method and my B, -4 times 7 is a -28. And I have to get to a positive 8. Is there anything that I can multiply to get 28 but subtract to get 8? I start thinking about it. I have 1 and 28, 2 and 14, and 4 and 7. None of those are going to give me 8. So at this point, I need to go to and use my quadratic formula. And you remember the quadratic formula is x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And I plug everything into that and simplify. So I have x is equal to, and I go and rewrite my formula, leaving blanks everywhere there's an a, b, or c. Go back and plug in my ABCs. B goes here and here. A goes here and here. And C goes here. Now doing a little bit of arithmetic. I have -8 plus or minus the square root of 64 plus 112 over -8. -8 plus or minus the square root of 176 or -8 point. You can go and grab a Desmos calculator and we can take and plug these into our equation here. I have -8 plus the square root of 176. All of that making sure I put that in parentheses here to here, divided by -8. That one gives me a negative answer. So I want to go back up here and change this to a minus. And now I have a positive answer of 2.65. So I come on here, 2.5, 2.65. So my final graph will look something like this. Coming here and going down to there. At this point right here, the ball hits the ground. Applications of quadratic functions. They're a good thing.